Hello team, today we're going to look at transformations of graphs. We have previously looked at something along this lines where we've identified h and k values when we have the general form or turning point form of quadratics, point of inflection of cubics, etc., hyperbolus, truncus, but we're going to look more in depth and more rigor at what transformations are and how they can be represented both algebraically in coordinate or function form. We're then going to use that to apply transformations to functions, and then also if we have, when we start with, say, some original function, we're given some new version, identify what are the transformations that take us from one to the other. So let's jump straight into it. As part of this, we're going to have a lot of new language that we're going to use, so bear with me as we work through it all, but we need this to be precise and consistent with when we communicate about transformations. So when we perform a transformation, it's useful to think of them as some image. Think of it graphically. So there's some image, in this case our red line, and then that image under some transformation, or some transformation has occurred to it. So we've taken our red line and it's been transformed into the blue one. So start with some image or picture and we transform it into another. The key thing is this can happen not just with lines but with any single coordinates, and it may also help when first getting into this to think as individual coordinates rather than whole functions. But as an example, as I was saying here, we have a relationship that is y equals x squared in the red line, and the blue line is an image of that relationship, okay, that has been translated 2 units in the positive x-axis and 4 units in the positive y-axis. So it's been translated across 2 units to the right, and it's also been translated 4 units up, and we can see that tracking each of the individual coordinate points within that quadratic. It's really common to be asked to find the equation. So the new rule or relationship for the image of some curve, the old rule relation undergoing some translation, which is a map. Okay? So we start with some image and we map it following directions to some new image. And those instructions can be all of our transformations. They can be translations, reflections, and dilations. Now we know, if we've been up to date and paying attention to everything, if we look at y equals x minus 2 squared compared to just y equals x squared, this function here, the x minus 2 all squared, is translated 2 units in the, and hopefully you should be very quickly able to fill in these blanks, in something direction of what axis? Well, looking at this, we can say h is 2, thinking about our turning point form of a quadratic. So that means it's 2 units in the positive direction of the x-axis. We know it's translated 2 units to the right. And by this stage of year 11, you should really be able to say that looking at that equation. But what if we're asked to prove it, or say why? Why is that the case? Well, we need some more notation. We need some symbology to help explain or to communicate mathematically. Rather than just speaking words, let's write it out. Okay, and we're going to look at 2 main notations. One is coordinate notation, when individual coordinates that can be mapped to any function. And we will also look at what we call a transformation function notation. But to describe a translation mathematically or symbolically, we need to think about individual ordered pairs, or a coordinate, because whatever transformation is being applied to one coordinate on a function, in this case here, it's the same that's being applied to the rest of it. So if we can think in terms of a single coordinate or all old coordinates, it's much easier to think that way. Oh, sorry. Here we go. So, if I was to move a set of coordinates 3 units to the right, what would the new coordinates be? Well, if we have some old coordinates, x, y, they are moved to, the x coordinate is moved across 3, and the y coordinate hasn't changed. So we could say all the points x, y are mapped to x plus 3, y. Pretty straightforward. So we can take this a little bit further though, and we want to give these new coordinates a name. So the new coordinate symbology that we want to use, we generally refer to them as dash, because they have these little dashes here, and these are going to be different to dashes when we get to differentiation and calculus and all that, but just for now they're going to be dealing with transformations. So all our old coordinates x, y are moved, or a good word here is mapped, okay, to new coordinates x plus 3, y, and we call these the dashed ones, equals x dash y dash. So in this case, x plus 3 is equal to x dash, and y is equal to y dash. So we can see our y coordinate has not changed in this situation, but our x coordinate has been moved across 3. And here's a couple more visual examples. So we're starting with the dashed blue line, and we'll look at this one on the left here, and we can see that the coordinates have changed. X has been turned into x plus 1, but y has been left the same. So in this case, the point x, y is mapped to x plus 1, y. And we can write that using this notation. Same here on the right-hand graph, we can see the dashed blue line in this case has been translated down, and it's been translated down by 1 unit. So x, y has been, reading this line here, x, y has been mapped to x, y minus 1. And in both those cases, we could call those new coordinates x dash, y dash. Okay, and that gives us some notation now to talk about what are the transformations occurring. We're starting with something, we're doing some mapping that involves this set of instructions. Okay, so hopefully identifying what are the translations using this notation. How can we write translations? Well, horizontal translations are changes to the x coordinate, and vertical translations are to the y coordinate. So, for example, find the equation g of x for the image of the curve with the equation f of x equals x squared. So we're trying to find some new equation, which is some new image of some equation f of x equals x squared under the translation of 2 units in the positive direction of the x-axis and also 2 units in the negative direction of the y-axis. Okay, so really quickly we can think of, we don't even need to draw the shape, but we know we are going plus 2 to the right and also down 2. Okay. So what does that mean? How do we write that using this dash notation? Well, we start with our old coordinates, we do some mapping, and as we said, our x coordinate needs to go 2 to the right, and our y coordinate needs to go down 2, and we can call these new coordinates x dash and y dash. Equating the x dash with its x, so we equate the x component, sort of like equating coefficients. Think about it. The x dash is only related to the x bit, and the y dash is only related to the y part. Let's make this color a bit clearer. We have this sort of equating, so the new x coordinate, okay, is the old coordinate plus 2, and the new y coordinate is the old y coordinate take 2. That's all fairly straightforward, but I want to find what the new equation is. Now you might know, oh, it's a quadratic, it's turning point, I could just change the turning point form of the quadratic, put it across 2, down 2, and that's fine, but what happens if this is a 5th order polynomial or some other equation that we're not used to dealing with a turning point of a point of inflection form? We need to be able to use this information to get what the new equation is, and that is what these steps here are showing. Okay. Step 1, after we find our mapping, okay, so let's call this our mapping instructions. After we have those mapping instructions, we need to rearrange them to get the original x and y, the subject. We need to get the original x by itself and the original y by itself. And we need that because we're going to substitute them into the original equation. The original equation is in terms of the original y and the original x. what I can do is substitute that in. Okay, so let me write out the steps. So 1, we need to get our mapping instructions. 2, okay, write in terms of x and y, okay, the original x and y. Step 3, we're going to sub into original equation, and we can see that is happening here. Okay. We've put that y plus 2 in for the y, and we're going to put this x dash minus 2 in where the x is, and we get this equation here. Okay. The y dash plus 2 has gone in the front, and the x dash minus 2 has gone in underneath the square. And from there, we can rearrange this to just get y dash by itself. So that's our step 4, is rearrange, okay, to get y dash by itself. Okay, and now what we have here is some equation that's in terms of x dash and y dash, which we said by definition is our new x value and our new y values. That's our mapping. Coming back here, that's our new spot. That's our new spot, is our x dash and y dash spots. So we have an equation written here that is y dash is equal to, bracket, x dash minus 2 all squared minus 2. And we know from turning point formula quadratic that that's right. H is 2, k is minus 2. We've gone across 2, we've gone down 2. The last bit we need to do is we're asked to find it called g of x, so we just need to now rewrite it. Instead of y dashes and x dashes, it's some new function called g of x, and since it's g of x, not g of x dash, our x dash gets changed to just an x. It's a different x to what was up here. That was f of x. This is g of x. So that's our process for using the dashes or coordinate notation to find out what some new equation is under some transformations. And this steps hold true for when we look at all other transformations, when we do reflections and dilations. It's step 1, get our mapping instructions. Step 2, write in terms of the old x and y. Step 3, substitute into the original equation. And then step 4, to rearrange to get y dash by itself. And then sort of step 5, write with the proper name. So, if you want, pause to have a go at this one. Otherwise, you can follow along. So, write down the equation of the image when the graph 1 on x squared is transformed by translation 5 units in the positive direction of the x-axis and 2 units in the negative direction of the x-axis, negative direction of the y-axis. So we're starting with some original coordinates, x, y. We're applying a map to them, and in this case, x coordinate is transformed by translation 5 units in the positive direction of the x-axis. So that is moved across 5, and the y coordinate, 2 units in the negative direction, is moved down 2, and that is equal to our x dash new coordinates. So we can say x dash is equal to x plus 5, and we have y dash is equal to y minus 2. So we've got our mapping, we've effectively equated the coordinate pairs. Our x coordinate relates to each other, our y coordinate relates to each other. And from here we need to go back, we now need to write in terms of x and y. So our original x and y, we need to rearrange these. So this is going to become x dash minus 5 is equal to x, and y dash plus 2 is equal to y. So that's done. We've done our mapping, we've got it in terms of the original x and y. That means we can substitute into here, we can say this is y is equal to 1 on x squared. So I can substitute this bit in for x and this bit in for y. So I'm going to get, it follows on that y dash plus 2 must be equal to 1 on, and we've got to replace the x itself, do the substitution, so it's x dash minus 5 all squared. And from this we can go y dash is equal to 1 on x dash minus 5 all squared, take the 2. Yeah. And if we want to, let's call it, we're not asked to give it a name, but let's call it, we'll say g of x is equal to 1 on x minus 5 all squared minus 2. this graph here, and you could check with your CAS calculator. You write that one in your CAS or Desmos, and you put this one in your CAS. You'll see that this one is 5 units to the right and 2 units down. And again, this is just a truncus, and we can see our H and our K value here. H is 5, K is minus 2. So that works. Right here. That is using coordinate notation. This method will always work, and it's fairly intuitive because you're just thinking about, I have some coordinates and I do a bunch of instructions to them. It's very hard to get that wrong. The thing is that we notice a pattern, okay, and we've already noticed it because we've been using it to look at point of inflection form, turning point form, all of those. Our H and K values is that, especially for translations, if it's 2 units across, or 5 units across in this case, write a -5 there. If it's 2 units down, put a -2 on the end. This pattern always comes out, so surely there must be some way that we can actually write this and know that this will occur 100% of the time. There must be some algebraic way. So what we can use is some transformation function notation instead. Okay. And this is working in more general terms. Okay, and I'm going to use this slide to try and hopefully prove why this is the case. Okay, so we've said that, go back to our original thing that we can intuitively look at, x minus 2 all squared is y equals x squared, translate 2 units in the positive direction of the x-axis. Okay. Let's think in general terms now. Let's think of this as a h. Okay, so we can use parameters. We can think of a h, and we can even think of the plus k on the end. Why is that always the case? Why does that h appear there inside the square, and why does the k always end up at the end? So how about we have some map, okay, where we have some original coordinates, okay, and the instructions is to just go across some h and go across some k. What's going to happen if we follow those instructions? Well, we get our x dash equals x plus h, and our y dash is y plus k. So that's step 1. We've got our mapping instructions. Step 2, we need to write it in terms of our original. Okay, get original x and original y by itself. But we don't have an equation to substitute into. But we always know, okay, thinking function notation, that f of x can represent any function. So how about instead of substituting into y equals x squared or y equals x cubed or whatever it may be, well, we can represent we can catch call all of those, okay, by just saying, well, just leave it as f of x. So we can replace our y with y dash minus k, which we do here, and we can replace our x with x dash minus h. And rearrange to move stuff to get y dash by itself and call it its new name. Okay, so 3, there's our step doing the substitution, and we end up with g of x, whatever our new function is, the old function, writing minus h wherever there's an x, or writing x minus h wherever there's an x, and then plus k in the end. And that's going to hold true for any function for any translation. In this whole slide, we've just used parameters. There's no explicit set number. We're going across some h, we're going down or up some k, and here the trick is we've applied it to any function. So we get this generalized rule that acts as a bit of a shortcut, and that's what we've been using all this time. Okay. For point of inflection form, turning point form, asymptotes of truncus and hyperbole, that sort of thing. Okay. If we can recognize there's an x minus h inside the function, per se, and then a plus k on the end, that's translations, and that's always going to be the case. So if you're asked to apply transformations, you can use this as a bit of a shortcut. So this takes us to our second method. This method back here, we're going to call the dash method. Okay, hard to make mistakes, takes a little bit longer. If you understand this function notation or the shortcuts that come from it, we get a second method. So using a function notation, or what I'll generally refer to as just using inspection, just knowing that this pattern always holds true. So if you ever translate h in the direction of the x-axis, you get this sort of mapping. which means that you always just have to replace x with x minus h. Same thing if you do a translation of k in the y-axis. This mapping occurs where it's f of x plus k, so you stick a plus k on the end. So the shortcut is just whatever the function is, put a plus k on the end. So if we remember important these two shortcuts here for translations, then you don't have to do any of the dash method working out. So for example, the function f of x equals x cubed is translated 2 units to the right and 1 unit down. Give the function g of x. Okay, well, I'm 2 units to the right, so I need to replace x with x minus h. So my h in this case is 2, and 1 unit down, so in this case my k is minus 1. So following these rules, wherever the x is, I'm going to replace it with x minus h. So g of x is going to be equal to, instead of the x, well, I have to put x minus 2, because there's a minus here. Okay, and then whatever my h value is, and then I need to put a plus k on the end. Now my k is minus 1, so I could write, just to show what's happening with the signs, plus the minus 1, which is the k, that's our k exactly. So this simplifies to, and that's it. Don't need to do any dash, don't need to rearrange, don't need to do, we are doing substitutions, we're doing shortcut replacements. But that's a lot quicker than all of that working out. So let's have a go. We're going to use this 2 different methods on the same problem so we can make a comparison and make sure that it is holding true. Write down the equation of the image when the graph of y equals square root of x is transformed by a translation 3 units in the negative direction of the x-axis. So there's one transformation, and 1 unit in the direction of the 1 unit in the negative direction of the y-axis. Okay, so we're starting with some original coordinates x comma y. We're applying a map, and our x-coordinate is being moved left 3 units, and our y-coordinate is being moved down 1 unit, and that gives us some new coordinates called x dash y dash. From here we can equate our coordinates, so we get x minus 3 is equal to x dash, and y minus 1 is equal to y dash. So that's step 1. Step 2, okay, we need to get in terms of the old x and y, so we're going to get x is equal to x dash plus 3, and we get y is equal to y dash plus 1, so that's step 2. Step 3, we need to substitute these into our original equation, which in this case is y equals square root of x. Okay, so it follows on that y dash plus 1 must be equal to square root x dash plus 3. Okay, and rearrange that to get y dash by itself, so y dash is equal to x dash plus 3 minus 1, and let's give it a name, h of x. Could use g of x, but I feel like being a bit different. There we go, there's a new function. Okay, that is the original function translated 3 units to the left and 1 unit down. Okay, let's use our function notation, okay, to write it out. Okay, f of x is being transformed into x is being moved 3 units to the left. Now this is the thing, okay, it's the minus the h, so technically this is happening, and then it's 1 unit down, so that's occurring. That's our mapping, and that's going to be our new function h of x. So our shortcuts, you don't even need to worry about writing this notation. I just wanted to show you the equivalence between these two, okay, and importantly that this is different because of the minus, but we're working on our 2 shortcuts over here at the right. Okay, these are the key things. So we're going to replace x with x minus h, so y is equal to square root. Instead of an x, h is negative 3, so it's negative 3, and then we stick a plus k on the end, and our k is minus 1, so minus 1, so we get, let's come over here, y or actually no, we called it h of x. H of x is equal to square root of x plus 3 minus 1. And we've got the same. Okay. Realistically, when you get good at this inspection, you jump to just writing this. And that's fine. And unless the question explicitly asks for a certain method or is worth more than a mark, and sometimes even when they are worth more than a mark, all they're chasing is the two individual terms. They're not actually chasing 1 mark for working, 1 mark for solution. Unless it says an explicit method, then you just putting the answer is fine. Completely fine. Now, there is one issue with inspection, or two issues really. You have to remember these rules, and these rules add up. There's going to be these shortcut rules for reflections and dilations as well. And also, we've got to be very careful when we're doing this replace, like this word replace or substitute. You've got to replace exactly the x. In particular here, doing this rule, people run into issues. So for example, and this is what I mean by we only need to apply to the x value itself or replace just the x. Let's have a look at this example. Write down the equation of the image of the graph, x on 2 all squared is transformed by translation of 5 units in the negative direction of the x-axis. Okay, so in this case, h is minus 5. Okay. And we recognize that we want to replace, okay, we want to, if I can write, we want to replace x with x minus h, which in this case is x minus negative 5, which is x plus 5. We want to replace x with x plus 5. Now we need to replace just that x. Now that x is divided by 2, so we can see here, okay, that the whole of x plus 5 must go in the numerator. You cannot write what is down here. Okay. In this case, you haven't replaced x with x plus 5. You've put plus 5 next to x on 2. It's very different. You've got to think about this x acting like a box, okay, a placeholder, and in that place, whatever else is happening to it happens after that x, so we need to replace that x with x plus 5. Okay, so down here, that is wrong. So here's another really quick example. Write down the equation of the image when the graph of y equals x on 4 all squared is transformed by translation of 3 units in the positive direction of the x-axis. So in this case, h is 3. So I'm going to replace the x. So this is going to be y is equal to x. Got to replace exactly this, minus 3 on 4 all squared is the correct way. That is correct. The wrong way would be y is equal to x on 4 minus 3 all squared. Wrong. Okay. Rightio, let's have a look at dilations. A dilation of the graph can be thought we're stretching or shrinking towards an axis. Okay, so and there's two ways that this can be stated in the study design. One is from an axis, okay. The other is parallel to an axis, okay. So in this case, this picture here, and I don't have a camera to show you what I'm doing with my hands, but we're pulling the graph up and down. So we're actually dilating from the x-axis. We're pulling away from this x-axis. Okay, so that's what dilation from the x-axis means. Okay, is we're stretching away from it, both up and down. This can also be referred to, though, as parallel to the y-axis. I'm pulling parallel to the y-axis. I'm pulling up, I'm pulling down. So both those phrases mean the same thing. And they mean what is demonstrated in this picture, pulling up and down. Okay, in this case, okay, it's quite obvious to note if we think about what's happening to an individual coordinate. In this case, we've dilated by, I haven't actually written by a factor, oh yes, by factor A, in this case placeholder A for any dilation amount. In this picture here though, okay, we can notice what's happened to the y coordinate. It has been doubled. Okay, so this has been stretched up by a factor of 2. We can think, in our case, I had x, y, it's being applied, the x coordinate hasn't changed, and the y coordinate has just been doubled. And that gives me x dash comma y dash. Okay. In this situation. So in general, we can represent it by x comma ay. Now, if you want to go through the whole process of doing this, okay, the generalized parameter form of the transformations, do the substitutions, rearrangement, and all that, you can, but I'm not going to go into the proof. But what comes out of it, okay, this here is our function notation for the transformation. This is the matching thing. What always happens, okay, is that A ends up at the front of the whole function. Whatever that function may be, doesn't matter how small, simple or complex it is, if you dilate by a factor of 2, then every y coordinate has just become twice as big. So whatever that value you get out of this whole function, well, just multiply it by whatever your dilation factor is. So here's our coordinate notation. And here's our function notation. And I'll write what the exact shortcut is on a later slide. If we dilate from the y-axis, okay, we're going to talk by a factor of b. That's going to be a placeholder instead of h and k. We're using a and b's for dilations. Okay, we can see, okay, from the y-axis we're stretching away. Okay, from the y-axis in this case, our x-coordinate is 2 times further across. Okay, so for this image, this actual mapping, our x-coordinate is twice as far across, but our y-coordinate is the same. And that gives us this coordinate notation. Same thing, this can also be referred to as parallel to the x-axis. We're stretching parallel to the x-axis. So there's 2 ways to refer to each of the dilations. And again, if you want to go back and do the generalized parameter substitution into any f, like substitute this into any f of x, we get this as the function notation. Now that's a little bit odd. Why is it f of x divided by b? I'll give you a minute to think about it. You can pause if you want to try and figure out why. But it's really interesting. And we need to think of a function as an input and output, cause and effect, that sort of thing. If we come back and look at our graph, let's look at this situation here, this coordinate. At one spot I'm putting in a value, let's just say that original value that was x equals 1. And then this value, which is twice as far along, that is x equals 2. How can I was originally putting in 1 and I was getting some y value. Let's say that y, it's a perfect circle, so let's say that y value at that point is 1. In that function, when I was originally putting in 1, I was getting out a value of 1. Now, I want to be able to put in, and this is the odd bit where we need to change our thinking, I'm actually trying to put in something twice as big. My input has grown by 2, but my output's still the same. How is there any way that I'm going to be able to put an input twice as big but still have input be the same? Well, the only way that you can do it is as soon as you put that input in, I need to, in this case, I would need to halve it. Okay, I'd need to halve it, and then all the rest of the function will then spit out the same number. I need to turn this x equals 2 into an x equals 1 compared to the original function, if we think in terms of the original function, to get the same y value. So that's why in this case, when we do dilations from the y-axis, okay, because we're actually making the x-coordinate twice as large or 3 times as large or whatever it is, but we still want the same y-coordinate, well, we need to cut down that input. We need to reduce that input because we've put in a larger input. We need to turn it back to the original size, the size of the original one, so we get the same output out of the function. So that's why that's actually division. So let's do some dash method work, doing some dilations, because dash method is always pretty intuitive. The coordinate's being changed, so you just write how much the coordinate's being changed by. You don't need to worry about what's the relationship between input and output. That's where function notation is important. So we've got an example on the left, and then you contrast and compare as you can have a go at the one on the right. Again, pause where you need to have a go first before I go over it. but determine the rule of the image when the graph of y of x is dilated by a factor of 2 from the x-axis. Okay, so in this case, oh no, I'm trying that wrong. That's from the, oh no, go back. Okay, we are dilating from the x-axis, so we're stretching it up and down. So in this case, our y-coordinate has been doubled by a factor of 2. So we just follow our dash method process. That's the change that's occurred. Get our mapping. Okay, right, and that's step 1. Get it written in terms of the old x and y. Do the substitution. Here's our new equation, step 4. So let's do from the y-axis. So if we're dilating from the y-axis, we're stretching away from the y-axis. So we're stretching this way. So what's actually being impacted is our x-coordinate. So our original x and y coordinate are being mapped to some new coordinate where our x-coordinate is being modified by a factor of 2. And we get a y-coordinate, and we can call that x dash y dash. From here, we can equate our coordinates, so 2x is equal to x dash, and y is equal to y dash. Rearrange to get the original y and x by itself, so we get x is equal to x dash on 2, and well, y is still equal to y dash, no changes. Substitute that into the original equation, so it follows on that we get y dash is equal to the square root of x dash on a half. And as you can see here, even though we're dilating by a factor of 2, because we're from the y-axis, our x-coordinate is changing, it actually ends up looking like a division. So that proves that this holds true. Okay. And let's call this g of x for the sake of it. Okay. So this division, even though it's unexpected, does hold true, as we've just shown. So if you want to use the shortcuts, if we dilate from the x-axis, okay, it's really simple. Stick the dilation factor in front of everything. Okay, whatever the whole function is, okay, and I could even put brackets around that, just multiply, and that is actually important. If there's already some translations or whatever being applied, you have to multiply a by everything. The whole function is being made twice as large, or 3 times as large, or a quarter the size. Dilations can also be fractional. In the case of from the y-axis where the x-coordinate is changing, you have to replace x with x on b. Okay, so let's use them really quickly. Determine the rule of the image when the graph of y is equal to square root of x is dilated by a factor of 2 from the x-axis. So we're dilating from the x-axis, so we just have to stick the dilation factor at the front. So y is equal to 2 root x. That's it. And that matches back here. Tick, tick. Okay. From the y-axis, so our dilation factor of 2, we have to replace x with x on b, so we get y is equal to the square root of x on 2. And that's it. Okay. Again, we have to be careful with this because we're replacing x, which is normally inside, have some other operators applied to it. You have to replace exactly the x. Okay. You wouldn't, this is correct, you wouldn't want y is equal to the square root of x all on 2. No good. Okay. You haven't replaced the x itself. Rightio. So that's what I've talked about. I'm going to leave them for you to have a go at, just for the sake of time. But we're going to look at reflections, and we'll finish this video here. This will have to be split into 2 parts because there's quite a significant amount of content. So reflections, when we reflect in the x-axis, means we are flipping about the x-axis. So what's happening to the coordinates? Well, the x-coordinate stays the same, the y-coordinate is just made negative. So that's what we can think of in terms of our mapping. X-coordinate stays the same, y-coordinate is made negative when we reflect about the x-axis. So an example here, find the equation of the image after y is equal to 1 on x squared is reflected in the x-axis. Okay, so since we're reflecting about the x-axis, the y-coordinate is made negative. That's equal to our x dash y dash. Equate coordinates, rearrange to get the x and y by itself. In this case, it's just moving the negative sign is the one thing that's happened. Notice that the y dash now has the negative sign. Substitute those into the equation and then rearrange to get the y dash by itself, and you end up with something like this, because the step after here, you get y dash is equal to negative 1 on x dash all squared. And there we go. Reflections in the y-axis, okay, very similar. Okay, it's just the other coordinate's being changed. If we're reflecting about y, we're flipping left and right. The x-coordinate is made negative, but the y-coordinate stays the same. So this is our mapping. X-coordinate made negative, y-coordinate stays the same. Okay, so find the equation of the image after y equals 1 on x is reflected in the y-axis. So x-coordinate is made negative, equate coordinates, rearrange to get the x and y by itself. So you can see here the negative sign has moved to the x dash. Substitute in to the original equation, and we can write this in many different forms. 1 on negative x is the same as negative 1 on x is this negative of 1 on x, and then negative 1 all divided by x. All of those are the same, and that's a key thing to recognize about the hyperbola. Okay, because 1 on x is a hyperbola, looks like this. If we reflect in the x-axis, okay, reflect about the x-axis or reflect in the x-axis, okay, if we flick this way, okay, we end up like that. But if we reflect about the y-axis, so if we are flipping it this way, well, we end up with, look at that, those two are actually the same. And that's a special case with hyperbola, okay, if it's not translated. If it's got translations, then all of that gets impacted. Because, yeah, I will leave it for now. Don't want to confuse you. But when you reflect a hyperbola about the x or the y-axis, you get the same result, as long as it's not being translated. So what are the shortcuts of function notation? Well, replace x with negative x when you reflect about the x-axis. And if you're reflecting about the y-axis, replace all of fx or put a negative in front. Put a negative in front of the whole function. Because you think about it, in this case, if you reflect in the x-axis, hold on, have I written those around the right way? Yes. Yeah, that works out. Okay. Yeah. Okay. So, really quickly, let's have a go. Determine the rule of the image where the graph of y equals 1 on 4 is reflected in the x-axis. So this just becomes 1 on, replace the x itself, negative x all cubed. Okay. Which in this case, because of a negative, not cubed, to the power of 4, a negative to an even power will actually become positive. So in this case, it is going to become the same. It actually stays the same graph, because 1 on x to the 4 is just a steeper version of a truncus. So if we reflect that about the x, hold on, what am I doing wrong here? There's something I reckon I've put wrong on this slide. Let's come back here. And this is where, when something doesn't match what you expect, because if we reflect in the y-axis, this should stay the same. It looks exactly the same. But if we reflect in the x-axis, the graph should look different, so we shouldn't have the same equation. So have I got something wrong in my notation up here? And by up here, I'm talking about my shortcuts. When we reflect in the y-axis, the x value changes. I'm pretty sure I've put these around the wrong way. Yeah, I put them around the wrong way. Yeah, if we reflect in the x-axis, that every y-coordinate is just made a negative version of it. Yeah, so that's my error, okay? These two need to be around the other way. And there we go. That's how we can always check our thinking. So in this case, this should be y is equal to negative. Put negative in front of the whole thing, which just gives us negative 1 on x to the 4. Very good. Okay, reflect in the y-axis. As I said, we get y is equal to 1 on replace the x itself, negative x to the 4. Since it's to the even power, that just becomes x to the 4, which makes sense. We reflect in the y-axis, those two things flip about, and that just still looks the same. Find the equation of the image after y equals x plus 2 is all squared, is reflected in the x-axis. So reflect in the x-axis, we put it just negative in front of the whole thing, so this becomes negative x plus 2 all squared. And if we reflect on the y-axis, we replace x with the negative x, so this becomes y is equal to negative x plus 2 all squared. Some people, by convention, don't like to start a bracket or the term in a bracket with a negative if there's a positive option, so some people will rewrite this as 2 minus x all squared. Either one of those is correct. Rightio. We're going to leave it there because that's a really long video. So in part 2 we'll look at if you're applying all of them at once, okay, which you end up with this full coordinate notation of that, dilation, translation. There's also tied in there, you can put reflection, same here, dilation and reflection, and then translation in there, or the giant form of function notation. We will also look at determining, so if you're given the original function and what the final function is, we'll look at figuring out what the transformations are to get there, and that'll be covered in part 2. As always, if there's any questions, stick them in the comments below or on Google Classroom. Thanks and see ya.